All right, ladies and gentlemen, welcome to Certificate Bypass, Hiding and Executing Malware from a Digitally Signed Executable with Tom Neprovsky. You're in South Seas IJ, so if that's not where you intended to be, well, it's too late. Enjoy the talk. A couple of quick announcements. Stop by the business hall if you haven't already, located in Bayside AB, sometime during the day, or for the welcome reception tonight from 1730 to 1900. Also, the Black Hat Arsenal is on the Palm Foyer on level 3. That's the level we're on here. A lot of good stuff there. Join us for the Pony Awards tonight in Mandalay Bay BCD. That's on layer 2 down below us. That's at 1830. And then also, if you haven't already, please put your phone on silent. That helps the rest of us ignore your calls while you wait for voicemail to pick it up. At this time, Tom, it's all you.
Okay. Thank you very much. First of all, I'd like to thank each and every one of you for coming for my briefing, and thanks especially Black Hat for giving me the opportunity to be here and the opportunity to give you this presentation. First of all, a few words about me. My name is Tom Neprovsky. I began my journey in the cybersecurity world back when I was a teenager. And at the age of 18, I was recruited to the intelligence department in the intelligence corps of the Israeli Defense Forces. I was there for 5 years. Later on, I joined Verint as a security researcher, where my main role was to develop sophisticated intelligence systems, which were being sold to governments and intelligence agencies. And 1 year ago, I joined Deep Instinct, which is the first company to apply deep learning to cybersecurity, also as a security researcher, where my main role is to develop sophisticated attack vectors in order to challenge our product and make it more resilient to different kind of attacks. So the outline for today's presentation, first of all, will be a drill down to the relevant fields inside the P file, which is related to file signatures. I'm going to go into an analysis of how exactly Windows loads and executes P files, and we'll cover the concept of a reflective payloader, and we'll demonstrate how we wrote a reflective payloader from scratch in Deep Instinct. And I'll finish the presentation with Deep Instinct recommendation on how to prevent this kind of attacks, and the demo showing you how we bypassed security solutions on the market using this kind of attack. So first of all, let me ask you the following question. Can you trust, and when I say trust, can you really trust a digitally signed file? Well, it depends. On what? Let's see. So first of all, as you can take a look on the screen, this is a structure of an average P file, which does not contain any certificates. But in case we have a certificate inside the P file, we have a table called attribute certificate table. And from now on, I'm going to refer to this table as ACT. This ACT contains information such as the PKCS #7 and the X509 information. And inside this table, we have the hash of the file. The hash of the file is calculated by Windows, and then Windows knows that the file has not been tampered with before. So in order to know that we have an ACT inside the P file, we need to take a look at the image optional header. And in this header, we have a data array called data directory. And this array contains 16 elements, and each element is giving us information about different structures inside the P file. And each element inside the data directory contains 2 fields. We have the size, which is the size of the structure we are referring to, and the virtual address, which is the address of the structure inside the P file. So in order to know that we have an ACT, we need to take a look at an element called security directory. And the security directory is giving, as I mentioned before, the size and the address of the ACT. But how exactly Windows calculates the hash for the file? It calculates the hash for the entire file except 3 fields. We have the checksum, the security directory inside the data directory, and the ACT itself. So we can exploit this and append additional information to the attribute certificate table while maintaining a normal execution of the file without damaging the hash of the file. So how exactly we are appending data to the ACT? First of all, we need to append a malicious code to the end of the ACT. For this example, the payload PE is not encrypted. Next, we need to change the size accordingly to match the new size of the payload PE. We need to change the size on two places. We need to change the size on the security directory, and we need to change the size on the ACT itself, because the ACT is a Win certificate structure which contains information such as the size of the ACT. And lastly, we need to change the checksum to match the content of the payload PE. Can anyone guess how many detection by antiviruses and security solution on a signed file containing a malicious code? 0 detection. None of the security solutions we tested on detected the signed file as a malicious one, even though it contains a malicious code inside its ACT. So what can be achieved using this kind of steganography? First of all, we get a persistency. No security solution, as I mentioned earlier, detected the malicious file, even when the malicious file was not encrypted. Second, we get stealth. The malicious file is inside a valid digitally signed file. And third, we have the ability to replace key files in Windows in case you have permissions, such as kernel 32, while maintaining normal execution of the file. So let's take some examples. We can use this kind of steganography. First, we can hide shellcodes inside the ACT and execute it using a special loader. Second, we can hide sensitive information, such as backdoor information inside the ACT. And lastly, what we chose to implement in Deep Instinct is a reflective payloader. But what exactly is a reflective payloader? Reflective payloader is the ability to execute PE files directly from memory and not from the disk. But the problem is that this concept is poorly documented in Windows, and this is why we decided to make an intensive research, and Deep Instinct wrote a reflective payloader from scratch. So before I'm going to go into details about how exactly we wrote the reflective loader and how it works, I need to set two key terms. First of all, we have the host process, which is the reflective payloader itself, and we have the payload PE, which is the malicious code inside the ACT. So before we can go on and parse the payload PE and extract additional information required for execute it, host process needs to read the content of payload PE from the ACT and load it to its memory space. Now that host process have payload PE inside its memory space, first of all, we need to validate that payload PE is a valid PE file. And we are doing this by 3 simple steps. First of all, extracting the eMagic field from the DOS header. Second, extracting a pointer to a structure called image_header and comparing the signature to the string PE:\0. And lastly, we need to make sure that the file is a 32-bit file, because at the moment, the reflective loader supports 32-bit files only. So now we have a valid PE file. Next, we need to extract the base address of host process, and we are doing this by extracting the image base address from the process environment block. And we need to do this because later on the following steps, we need to do calculations on memory spaces based on this address. So now the image base address is stored. The next step is to make sure that host process needs to self-relocate itself. And the reason we are doing this is because sometimes payload PE has a field called image base inside its optional header, which tells the operating system what is the preferred address that payload PE would like to be loaded to memory. But sometimes this address is in the range of host process in memory. And if we will map payload PE to this memory space, we may override some of host process information. So just to make this clear, let's take, for example, host process image base equals 4, and host process size of image is 5. Host process memory space will be between 4 and 9. And let's take an arbitrary value. Image base of payload PE is 7. What will happen is that when we will load payload PE to the header 7, all the information between 7 and 9 of host process will be deleted and host process will crash. So now we need to check if we need to relocate. Yes, the next step is to actually relocate. But if not, we are just skipping the steps required for relocation and going for extracting relevant information from payload PE to map it to host process memory space. So how exactly we are mapping, how exactly we are relocating host process? First step is to allocate enough space to contain host process using virtual alloc function. Second, we need to copy the content of host process to the new memory block we've just allocated. Third, we need to update the function addresses by processing import address table of host process to match the new memory space of host process. And lastly, we need to apply image-based relocation by reading host process base relocation entry in data directory and update all the relevant memory addresses that needs to be updated according to the new memory space. So now, host process is relocated. The next step is to extract relevant information for mapping payload PE. And the information we need to extract is 4 fields. First of all, we are extracting number of sections from the image file header structure, which, as the name implies, is the number of sections payload PE contains. Second, we need to extract the image base. As I mentioned before, is the preferred address that payload PE would like to be loaded to. Next, we need to extract the size of image, which is the size of image including all headers of payload PE. And lastly, is the size of the headers. As the name implies, is the size of the headers of payload PE. Okay, so now we have all the information for mapping payload PE. The next step is to actually map payload PE. And we are doing this by 3 simple steps. First of all, we are using the function virtual alloc to allocate at a specific memory address space. This is the image base address of payload PE. Next, we copy the headers, and the size is determined by size of headers we started previously. And the last step is to copy the sections. And the number of sections to copy is determined by the number of sections we also extracted previously. So now payload PE is now mapped to the memory space of host process. The next step is to process the import address table of payload PE. And in order to process the import address table, we need to get information about the relevant structures of all the imports of payload PE. So first of all, we need to determine the address of image import descriptor array by looking at the image directory entry import inside the data directory. And image import descriptor is a data array, and the number of elements inside image import descriptor depends on the number of DLLs payload PE is using. So for example, if payload PE is using 5 DLLs, image import descriptor will contain 5 elements. And on this structure, we need to extract 3 fields. First of all, original first thunk, the name field inside the image import descriptor, which is the name of the DLL, and first thunk. Original first thunk and first thunk contains pointer to 2 identical structures from image thunk data, which is also a data array. In this data array, the number of elements inside this data array depends on the number of functions payload PE is using from the DLL we are referring to. So for example, if payload PE is using 2 functions of a specific DLL, the entry of the specific DLL in image import descriptor will have 2 elements of original first thunk and first thunk. Next, in order to get the name of the functions, we need to extract a pointer to a structure called image import by name, which contains the name of the function we need to import. So what do we need to do for each DLL? First of all, we need to load it to memory using the function load library, and we are doing this by extracting the name field inside the image import descriptor. Next, we need to traverse through original first chunk to retrieve the function's addresses. And the reason we are traversing through original first chunk, because the way Windows works, all the information that contains what we need to know about the functions is in original first chunk. And as soon as we extract all the addresses of the functions, we assign the function addresses to the relevant item inside first chunk. So now we are traversing through original first chunk to retrieve the function addresses, and Windows allows us to import functions from Windows in two methods, by ordinal or by name. So if we need to import the function by an ordinal, we are just reading the ordinal field inside the image thunk data. But in case we need to import the function by name, we are just getting a pointer to the structure called image import by name, which is pointed by address of data. I'm not going to go into details about how we determine if we need to import by an ordinal or by name, but if you'd like to get some more details, you can refer to my white paper on Black Hat's official website, or come to a Deep Instinct booth after this presentation. So now all the DLLs are loaded to memory, and all the function addresses retrieved. The next step, as I just told you, is to assign the function address to the proper place inside first thunk data array. So if you take a look on the screen, this is before the assignment. We have the relevant function, the relevant address of the function we just imported. And how the structure will look after the assignment is as follows. Now, first thunk data array will contain the actual address of the functions payload PE is using. OK, so all the function addresses retrieved. Now let's sum up what we have so far. First of all, payload PE is a valid PE file. Image-based address of host process was retrieved. Host process was relocated in case it was needed. The information for mapping payload PE was extracted. We mapped payload PE to the memory space of host process. All the DLLs required by payload PE is now in the memory space of host process. And we retrieved all the function addresses required by payload PE. But if you think that's enough, that's not enough. We need to do 3 additional steps. The first one is to change the memory permissions of payload PE to actually allow execution from this memory region. Next, this step is not always mandatory, but we need to fix the image-based address inside the process environment block of host process to match payload PE image-based address. This step is not mandatory because it depends on the malware. Some malwares in the world relies on this address to make some calculations into the file, such as the Zeus Trojan. And lastly, we need to calculate the entry point address of payload PE. And we are doing this by extracting the field address of entry point from payload PE image optional header, and using this offset from payload PE image base. Now everything is set. We can execute the file by calling the entry point. So how exactly we can, first of all, prevent hiding files inside the ACT of a signed file? First of all, we need to acknowledge the fact that the ACT is a Win certificate structure which contains PKCS and X509 information. With that in mind, we just need to parse the PKCS and the X509 and check if we have additional information. In case something left from the parsing stage, we know that someone appended additional information to the ACT of the signed file. Now let's see a demo of how exactly we bypass security solutions. But before I'm going to go and press play, for this example, we chose to execute the HydroCrypt ransomware, which acts as any other ransomware you know in the world. We know that HydroCrypt is installed, because once HydroCrypt is installed, it creates a value inside the run key, which tells Windows what executables it will execute once a user logs into the computer. And on the last screen, we can see some pictures which will be encrypted by the HydroCrypt malware. So first of all, as you can see, HydroCrypt is not installed on the computer. Next, you can see that the target file is actually a signed file. For this example, we chose to take a file from Microsoft Office. Next step is to append HydroCrypt to the ACT of the Microsoft Office signed file. And as you can see, the file is also signed, even though it contains a malicious content, which is not encrypted inside its ACT. Now, the next step is to enable the security solution. As you can see, the security solution is being updated to the date of when we recorded this demo. The settings and the configurations remain the same. We didn't touch anything. As you can see, everything is enabled. Nothing is disabled on the real-time file system protection, on the antivirus tab as well, and on the HIPS as well. Now, the next step is to scan the new file we have just created, which contains the malicious content inside its ACT. According to this security solution, this file is a benign file. The next step is to execute the original HydroCrypt. And as you can see, the security solution detects the file as a HydroCrypt. And the next step is to execute HydroCrypt. Excuse me. Sorry about that. So as we will see in any moment, we will execute HydroCrypt from the ACT of the signed file, and HydroCrypt will be installed, and the files will be encrypted. So now this is the actual execution of HydroCrypt from the ACT using our reflective loader. So now the malware is being executed and is being installed on the computer. And as we will see in any moment now, the files on the left side of the screen will be encrypted. Unfortunately, this security solution did not prevent this kind of attack, but it did detect a false positive on the help your files text, which is a file that contains information on how you can contact the person who encrypted your files. Unfortunately, it's not helping me so much because my files are already being encrypted. Now for Deep Instinct demo. First of all, we are injecting the malicious code to the ACT of the signed file. As you can see, Deep Instinct client immediately detected HydroCrypt as a malicious one. The next step, in case any hacker did succeed to put a signed file which contains malicious file inside your computer, Deep Instinct client prevented the reflective payloader from being executed as well. And because we are identifying a malicious content inside the ACT of a signed file, we are preventing the execution of the signed file as well. The reason that Deep Instinct client prevented all these files from being executed is because Deep Instinct technology, which is based on deep learning, prevented this kind of attack for two reasons. First of all, our technology is domain agnostic and opposed as opposed to machine learning. And second, we are not looking at a specific set of features. We are just reading the entire content of the file as raw data and not looking into any specific set of features. A few side notes before I'll finish this presentation. First of all, Deep Instinct is not an attacking organization. As opposed to that, we are a security solution company. This tool was developed solely for preventing sophisticated cyber attacks. And last, this tool is not going to be released, as you might know, due to potentially malicious usages when in the wrong hands. Okay, thank you very much. You are more than welcome to come to Deep Instinct booth.